Okay, let's get started in half a minute or so. Let me put my slides here. Okay, cool. Okay, I think we can get started in half a minute or so. Okay, that's better. I think it's working now. People can hear me, right?
Yes.
Okay. Okay, cool. Okay, well, welcome. This is lecture 22 of Digital Design and Computer Architecture. And we're going to start memory systems today. It's going to be a lot of fun. We have the remaining part of the course is dedicated to memory, even though memory is extremely important. We finally build up to it, if you will. And it's going to be interesting to cover for sure. And in this lecture will be more of an overview lecture for memory systems. So I'm going to cover why it's important relatively quickly, but we will go through a lot of slides, some of which you have seen actually in lecture 1 or 2, or maybe 3 as well. Now it may make more sense after we have covered the processing paradigms. So it's always good to look at something you have seen in the past again after you have learned a lot, because you may have a different perspective on it and maybe a better understanding of it as well. Okay, how do I get rid of this thing that's in front of me? Okay, let's put it at the bottom. Okay, so basically these are the readings for this lecture and next. We're going to cover memory hierarchy and caches. We'll start memory hierarchy hopefully at the second half of today. And these are readings from your books. Unfortunately, your books don't do a great job covering memory hierarchies. So you will follow through lectures more, I think. Even though the books cover them a little bit, especially the Harris and Harris in these chapters, they don't go into as much detail as memory really should be covered, in my opinion, especially in an introductory course. And actually, many computer architecture classes don't cover memory much, and that's a big mistake, in my opinion, as you will see hopefully soon, because memory is the real big bottleneck in the systems today, because we have focused a lot on processing and how to make processing better in our systems for decades and decades, for more than 70, 80 years of the history of the electronic computer, let's say. But memory has not received as much attention, and we will discuss perhaps a little bit of that as well in this lecture. And the recommended paper, which may actually become a required reading at some point, I'm thinking about it, where you can get an extra credit, is this short paper by Morris Wilks that introduces the idea of caching, essentially. Okay, but before we go into another extra assignment, this is your extra assignment, Amdahl's Law, just as a reminder. Hopefully you're doing it because it's easy credits, and you will also get to read a seminal paper that's written that has had a lot of impact on the way we think about computing today. Clearly, we covered Amdahl's Law in last lecture, GPUs, as well as the previous lecture, SIMD, but reading the paper will give you a different perspective as well. So before we jump into memory, I will motivate a little bit, but basically we're done with this. You have gone through many, many different types of microarchitectures and approaches to concurrency. Essentially, I also call these processing paradigms. These are really processing paradigms in computer architecture. And we have actually covered essentially almost all processing paradigms that are out there that have impacted the world today. For example, we ended up with the GPUs. GPUs clearly combine SIMD processing concepts with concepts from fine-grained multi-threading, and they clearly employ pipelining, etc. So they have a combination of these concepts. We covered systolic arrays, for example. They also use a combination of concepts, but they're very different. So hopefully you're familiar with many processing paradigms right now. And this is really on the processing side. We talked about memory always, but memory, we never focused on memory. So food for thought for you is to think about trade-offs of these different processing paradigms. As much as possible, we covered these trade-offs. But now that you know all of them, you can actually think about the different trade-offs that exist between the different paradigms. And last lecture, we ended with another food for thought. What is the difference between systolic arrays and GPUs? Which one would you use when? And I will throw in another thing, maybe do you what is better potentially for machine learning workloads going forward? Systolic arrays, SIMD processing, a combination of both? How can you take the best of these different paradigms to accelerate important workloads going into the future? And clearly, trade-offs span beyond just workloads, right? Trade-offs of these processing paradigms actually span all the way from algorithms to devices. Some processing paradigms are more friendly to some algorithms. Some processing paradigms put a lot of work on the compilers. For example, we discussed VLIW. VLIW's philosophy is basically putting all the work on the compiler, making the hardware as simple as possible. Clearly, they make different trade-offs across the stack, and these trade-offs affect the hardware designer's life. They affect the compiler and the programmer's life, and potentially the algorithm designer's life. We talked about systolic arrays, for example. You may need to change your algorithms to execute well on systolic arrays or GPUs, etc. So basically, it's important for you to think about the trade-offs, and there are many of these trade-offs clearly, which we don't have time to cover. But this is really good to understand the trade-offs, and some of these trade-offs may have made easier to develop some of the paradigms, and may have made harder to develop some other paradigms. For example, the abundance of applications that can take advantage of the SPMD type of parallelism, SPMD programming model we discussed, and that type of parallelism may have enabled GPUs in a much better way in the last decade plus. So basically, the fact that a processing paradigm is successful or not successful is always a question of not only technical merits, but also what is the status of the programming and algorithms that are out in the field, basically. If you have algorithms that can fit very well your hardware, and if your algorithms can be relatively easily be adopted into your hardware, that processing paradigm may be relatively successful. Whereas if you have to completely change your software 100%, let's say, and the entire software stack, compiler, programming language, algorithm, etc., at the same time, the processing paradigm may be harder to adopt. And we've discussed some of the examples of this, like Dataflow is a prime example, right? Dataflow at the ISA level is very difficult to adopt because, and it has not been successful, clearly, even though the concepts are technically beautiful and nice, and they have affected things in a different way. But as Dataflow at the ISA level was not easy to adopt because it required lots of changes from essentially every programmer in the world, right? So keep these trade-offs in mind as we go forward. Okay, now let us take a step back and think about what we are doing in this course. Basically, we're covering computing systems, digital design and computer architecture, and digital design and computer architecture apply not just to the processing unit, right? If you look at a computing system, it consists of computation, processing units, communication, interconnects, I/O, and storage and memory. And we have focused a lot on the computing paradigms, let's say. And as I said, this is a slide from earlier lectures, one of the earlier lectures, actually. I said we will cover all three components. And we have covered memory a little bit. It's true, we have covered the memory a little bit, but we have never focused on it. So now we're going to shift the focus on memory. And hopefully you know extremely well the processing side of things. I/O, we've always kind of covered and kind of not covered. There's a lot over there. It's clearly communication and interconnects between different processors, between processors and memory, between different nodes in the system are important. In your Verilog assignments, you're doing wires, for example, etc. But we're not going to, unfortunately, we're not going to have a formal treatment of interconnects unless we somehow magically have time toward the end of, in the remaining lectures, basically. But memory, I should say, memory consists of a lot of interconnects, and you will see that as well. Basically, you have seen it earlier, and I'm going to show a picture that you have seen earlier as well. Memory, to access the memory cells, you need to go through wires, lots of wires. And a lot of the memory latency is dominated by the interconnect latency. So we try to reduce that latency by reducing the length of the interconnects as much as possible. Okay, there's one question. Would a data flow architecture have positive or negative impacts on our current memory problem? So that's a good question. And I think I will leave that question to you, perhaps. But if you actually build a huge data flow machine, it will require large memory bandwidth as well, because there will be a lot of memory accesses that it will do. Remember, one of the problems with data flow at the ISA level was too much parallelism, right? You can expose too much parallelism in your system. And as a result, it overflows the hardware components you build into the processing units. And I think a similar problem exists with memory also, with data flow. And it's also very irregular. Usually you can extract very irregular parallelism in data flow using the data flow paradigm from programs. So you may actually be accessing memory in a much more irregular manner than we are doing today in GPUs, for example. GPUs are very good at accessing memory in a streaming manner so that you can exploit the high memory bandwidth, but memory systems are not designed for random access in general. So that's a very good question. I think combination of these processing paradigms and memory is also important to examine in terms of trade-offs. Okay, how will quantum computing affect these? There's a question from YouTube, apparently. That's a great question. I think it's a bit too early to tell. Quantum computing is still a little bit out, in my opinion, to build large-scale systems at least. But certainly that needs to be examined as well. How do you look at, how do you design quantum hierarchies? Whatever I've seen so far in quantum computing is basically people are thinking of using traditional memory systems like DRAM, we will talk about, well, we have talked about briefly earlier, as part of the memory hierarchy for quantum computing systems. But if you can increase your parallelism greatly using quantum computing, for example, your pressure on the memory hierarchy will increase as well. Okay, so now we're going to jump into memory, and that's going to be our focus. And first, I will motivate why it's very important. And some of these slides we have covered at the beginning, but again, hopefully with the current perspective you have after 21 lectures, you may have a different perspective. So memory is dominant in a modern system. So if you look at a system like this is circa 2006 AMD Barcelona. You have cores, only 4 cores in the system, as you can see, but the rest of the chip is really dedicated to memory, almost all of it. Caches, even cores. Cores have L1 caches, register files. These regular structures that you see over there are memories inside the cores. But outside the cores, you have caches, interconnect, other caches, other interconnect, memory controllers, memory interface to do the analog to digital conversion and digital to analog conversion, and to control the memory as well. Other interconnect and memory. As you can see, this is the off-chip memory over here. So you have a lot of on-chip memory, and you have a lot of off-chip memory as well. And I'm not even depicting the storage units, which is really part of memory as well. So basically, if you look at a system today, most of the real estate is dedicated to memory. And that shows you how important it is, right? And this is another example. This is another picture that we looked at earlier. And clearly, we don't have a lot of details on this, but even just by glancing at it, you will see how much memory there is on this chip. I don't have exact numbers clearly, but you can see that there are cores here, and they have 12 megabyte L2 cache. There are other cores, simpler cores. They have 4 megabyte L2 cache. There's a system level cache over here. GPUs, as we discussed last time, they clearly have large register files, large memories inside, and clearly there are channels to access off-chip memory as well. Okay, and maybe this is another interesting example. We've discussed this Cerebras' Wafer-scale engine. And when I introduced it early on in the course, I said that these folks wanted to accelerate heavy machine learning training tasks. And for that, you need very large computation and very large data storage. And they decided to build a wafer-scale engine to get both on the same chip, essentially. So they were able to get 1.2 trillion transistors, as you can see, and put 400,000 cores on it. But what's also important is they were able to get fast access to 18 gigabytes of on-chip memory at high bandwidth also. They report 9 petabytes per second memory bandwidth. This is much larger than the memory bandwidth you can achieve by going off-chip, because off-chip, you have to go through long, power-hungry interconnects that are relatively bandwidth limited. And it's impossible, at least today, to get 9 petabytes per second. But by bringing computation and memory together in a relatively tightly integrated manner on a huge wafer-scale chip today, they were able to fit a lot of the data that they need to train the machine learning algorithms on this wafer-scale engine. And again, so it's really not just about computation. We motivated it earlier in terms of computation, except for first lecture, if you remember. But it's really about computation and memory being close together at the same place. And this is the more recently announced wafer-scale engine, as you can see over here. And this is as you can see, it's 40 gigabytes of on-chip memory and 850,000 cores. So they've actually doubled the number of transistors. So if you ever wonder if Moore's law is dying or not, I don't believe we're at the end of Moore's law yet, even though there are a lot of contrarians that say Moore's law is already dead. I don't believe it's dead. And I think the Cerebras wafer-scale engine shows that, basically. This is 2019, 1.2 trillion transistors. And 2021, 2.6 trillion transistors. That's more than double. And the cores have doubled, and the memory has more than doubled, actually. As you can see, that's 40 gigabytes of one-chip memory. It can be accessible by 850,000 cores. Of course, these are machine learning accelerators. We talked about it in the GPUs lecture briefly. These are SIMD engines, actually, internally. And they have access to 20 petabytes per second memory bandwidth. So there's one question. What is a normal memory bandwidth for out-of-chip memory today? So it's really on the order of, let's say, 100 gigabytes per second. So a petabyte is clearly orders of magnitude larger than gigabytes per second, right? Off-chip memory bandwidth is on the order of, let's say, 100 gigabytes per second. If you're really designed extremely carefully, maybe you can imagine reaching terabytes per second, but petabytes per second is at some different scale, as you can see. So there's one question. Could you go 3D once you run out of 3D space to uphold Moore's law? So absolutely. And people are trying three-dimensional integration. I mentioned this maybe in first lecture, one of the first lectures perhaps, but certainly three-dimensional integration is one way to actually scale your computation and memory. And people are actually doing a lot of work in that right now. High bandwidth memory is, for example, today 2.5 dimensional, but it's going to be three-dimensional in the future. And there's a lot of work on getting monolithic three-dimensional integration of different layers. And there are a lot of good questions actually coming up. I didn't intend this to be a research lecture, but isn't cooling a problem in 3D? Absolutely. So whenever you go three-dimensional, certainly you're basically blocking the escape of heat. And as a result, you need to find new cooling methods. So temperature, thermals are a problem, absolutely. So there's one more question I missed, I think. Is active research being done on Dataflow architecture-based algorithms? And are there significant potential differences to common algorithms assuming sequential execution? So that question is, absolutely, yes, active research is being done, especially in the, if you remember, when we talked about FPGAs, I mentioned that putting accelerators on FPGAs is really about programming in Dataflow, because you're really putting the data flow of your accelerator, mapping the data flow of your accelerator on the FPGA, right? So there's a lot of work, research being done on how to map accelerators on the onto FPGAs in a data flow manner. And actually, some of the machine learning accelerators, ASIC type of accelerators, also are being looked at from that perspective. So it's really, from the specialized accelerator perspective, data flow is having another renaissance, if you will. People are looking at how to use data flow paradigm to accelerate things much faster by mapping things onto reconfigurable substrates or application-specific substrates. Okay, these are excellent questions. I mean, some of these are actually more research type of questions that we cover in our seminar course or master's course. I'm just motivating memory over here, but it's good that it's opening up a lot of these questions, because memory is a bottleneck in all engines, basically. Okay, so I find these examples really fascinating because clearly there is a movement and the machine learning workloads are straining the system so much that people are really trying these different paradigms where they can put memory and computation together on a wafer-scale engine, as you can see. Okay, I mean, there are a lot of questions on the wafer-scale engine also, right? How do you cool this, for example? How do you power this up? How do you handle the reliability issues there? Because there could be faults over here. And how do you actually isolate the faults when one machine learning accelerator is not running well because of faults? How do you actually ensure that it doesn't impact other computation that's going on? So there are many, many issues over here. What about yield, for example? Can you really get good yield by actually having a huge wafer scale chip? Those are questions that need to be answered, of course, and it's good that there are startups that are working on it, and there's research that's also happening on it. Okay, memory is, basically my point is memory is critical for performance, and we have seen it many times in this course. Just to remind you a little bit, even though we never really went in depth into memory, except for maybe register file design and flip-flop design, except for lecture 6, where we covered sequential logic, for example, we did talk about memory. For example, we talked about load-related stalls and pipelining. We said that even with one cycle magic memory assumption, a dependent instruction that comes after a load has to stall. So you have a one cycle bubble, right? Because memory access happens a little bit later, right? We talked about load store handling and out-of-order execution processors. We talked about out-of-order execution and its memory latency tolerance limits. If the memory latencies are on the order of 100 cycles, can you actually tolerate memory latencies easily? How do you build large-scale out-of-order execution engines to tolerate memory latencies? And more recent announcements, for example, by Apple, show that they have larger instruction windows than before. And one of the reasons is actually to tolerate memory latencies. We talked about VLIW paradigm. We said that one of the downsides of VLIW is statically scheduled, and you get stalls due to long latency memory operations. And it's very difficult for the compiler, even if it's a dynamic compiler, to anticipate these long latency memory operations, cache misses. We will talk a lot about caches later this lecture and in the next week. The compiler cannot anticipate these cache misses. As a result, it cannot schedule the code nicely around those cache misses. As a result, one of the big downsides of the VLIW, completely statically scheduled instruction streams, has been the lack of or difficulties in tolerating memory latencies. We also talked about how the compilers try to do memory bank disambiguation in VLIW. If you remember the Bulldog compiler, for example, that slide, we didn't go into, of course, how the compiler exactly does it, but this shows you in this processing paradigm, you really need to ensure that instructions that are concurrently scheduled need to access different memory banks concurrently. And we talked about a similar problem in SIMD processors, right? We said many memory banks are needed so that you can sustain a throughput of 1 word per cycle. Okay, that's assuming a vector processor. Vector processor maybe needs 1 word per cycle. But if you actually have a modern GPU, it's actually hundreds of words per cycle. So you really want to sustain very large memory bandwidths in today's GPUs, and we discussed this in the last lecture as well. And we also saw a very simple SIMD vector processing example where adding more ports to memory simply increased your performance by basically more than doubled your performance, right? If you remember that example. We talked about GPU register files and memory systems in the last lecture. And we also talked about fine-grained multi-threading to tolerate memory latency. So why do GPUs employ fine-grained multi-threading? One of the reasons is, of course, to keep the pipeline simple. They don't need to do dependency checks. They have a lot of parallelism. But whenever they stall for memory now, they can actually bring in different instructions from different threads every cycle. As a result, they can tolerate the long memory latencies that they have. But of course, if you do fine-grained multi-threading now, you have a lot of threads that are concurrently accessing main memory, and your memory bandwidth requirements also increase proportionately. So GPUs are systems that are really pushing the boundaries today. Well, of course, I've just shown you another system that pushes the boundaries, right, which is this Wafer-scale engine. But clearly, memory is a huge bottleneck in these systems where you have a lot of computational units that are generating a lot of requests into memory. Okay, so this is a coverage from the lecture. But now let me go into a little bit more into why memory is really important. Basically, there are multiple perspectives of it. Essentially, today, computation is really bottlenecked by memory. Important workloads are all data intensive, and I give you examples from machine learning, for example. But we've also looked at other examples, vector processing, etc. I'm going to give you maybe a couple of examples without going into a lot of detail. And these workloads require rapid and efficient processing of large amounts of data, and data is increasing at the same time. So machine learning models today are actually taking in much, much larger amounts of data. So today we can generate more data than we can process. So let me give you the application perspective. So again, this is going to be a relatively high level, but many people have done studies. And if you're interested, you can actually look at the references that I provide over here. There are many, many studies, many more studies than this also, that have looked at workloads, large-scale workloads that look like this: databases, graph processing algorithms, in-memory data analytics algorithms, and data center workloads also. I'm going to actually mention this paper later on to make the point more clearly. But basically, people have found out that memory is a big bottleneck in these workloads. And different aspects of memory are bottlenecks at different times: latency, bandwidth, capacity, and sometimes all of them are bottlenecks, actually. So other studies have been done on other types of workloads. Maybe these are more consumer type of workloads, right? We're actually using some of these workloads potentially right now on YouTube, for example. If we're doing streaming over YouTube, we're doing certainly video encoding and decoding, and browsing, and clearly machine learning frameworks, as we have discussed. And people have found out these are all bottlenecked by memory as well, especially when you get to large data set sizes. So once you get to large data set size, your memory becomes a big bottleneck. And again, different aspects of memory may be your bottleneck. And there are other workloads that people are examining and increasingly examining because they're going to be more important, as we discussed in the first lecture. sequencing, for example, genome sequencing, analyzing genomes, comparing different genomes. Imagine comparing millions of different genomes so that you can find patterns of disease or patterns of susceptibility to different things, or patterns of better drug response or vaccination response these days. That could be also interesting, certainly. So we need more of these studies, clearly. And again, in these workloads, because of the amount of data that you need to access, memory is a bottleneck. So computation, we've dedicated a lot of time over the last 70 years, and we've optimized a lot out of our computing units, but maybe we have not optimized a lot out of our memories. And just to make the point more strong, maybe if you look at these devices, these are nanopore sequencing devices. You can actually buy them for 1,000 to 2,000 francs today, maybe even cheaper right now, I don't know. And you can actually do sequencing in your hand. So this is how the sequencing technology has improved. Unfortunately, the memory bottleneck has not improved because the data movement out of this device and into this device, well, you don't normally do data movement into the device because the device doesn't have processing capability in it. But normally, people are actually using these devices to sequence genomes, let's say different virus genomes or different samples of anything that you can imagine. But they need to send the data all the way to data centers, and data centers actually execute genome analysis workloads, and they're all bottlenecked by memory and storage today. And you can read some of these papers that actually talk about this bottleneck. This is one paper that we have written, as you can see, that was published a few years ago. And this is actually becoming even smaller. You can actually buy these genome sequence analysis devices and attach them to your phone as well. And clearly, you can imagine the amount of data that you can generate that way. Okay, so if you're interested in this, I mean, I mentioned this earlier also in lecture 1, but we do a lot of research in genome analysis. That's why I keep talking about it, because I think this is going to be even more important to the future. And I think we are a little bit late realizing that today with the COVID-19 crisis, let's say, if we actually were ready to handle large amounts of genome sequencing, which we were not, clearly, then maybe we would have had a much better response to the COVID-19 crisis. But I think we need actually a lot more thinking about memory to actually accelerate genome analysis. And if you're interested, you can actually read this paper or watch this talk, which covers a lot into algorithms and hardware co-design with focus on reducing the memory bottleneck. And there are more lectures also. Okay, so that was the application or workload perspective. Clearly, workloads are demanding a lot from memory. And as a result, our performance is suffering. And let me give you the performance perspective also. I mentioned this, I think, in an earlier lecture also, but maybe this will become more clear right now, because this sentence, "It's the memory stupid," is coming from Richard Seitz, who was the chief architect of the alpha processors, the first out-of-order processors, one of the first out-of-order processors of its time, alpha 21-164 and 21-264. In fact, that was one of your readings, alpha 21-264 microprocessor. And Dick Seitz, after they designed this processor, he wrote a one-page article in Microprocessor Report. That could also be an extra reading, but let's see. This is easy. This is very easy to read. You can read this article, and basically in this article, his team designed the fastest processor of its time. And he basically says, we designed a processor that is 4-way superscalar. Now you know what that means, right? It can finish 4 instructions, fetch, decode, execute, finish 4 instructions per cycle. But on this important database workload, we found that it's finishing 1 instruction every 4.7 cycles. So basically, it's operating at less than 1/18th of its peak instructions per cycle bandwidth, right? That sounds terrible, right? It's about 5% efficiency, if you think about it, of its throughput, of its maximum throughput. And he basically says, why? Because it's waiting for data to come back from memory. And he finishes the article saying, I expect that over the coming decade, memory subsystem design will be the only important design issue for microprocessors. And I think he was right, but we need to do more still. Still, we haven't done enough, I think, because I'm going to give you some more results that are of this nature. So this is data from my own PhD thesis, actually. In my PhD thesis, we developed mechanisms to tolerate memory latencies in out-of-order processors. And we did some studies together with Intel, and we looked at all of the workloads that Intel was using to design their processors with at the time. And we found out essentially the same thing. Averaged across more than 140 workloads, the processor, the cutting edge processor of its time, is waiting for cache misses to come back from memory most of the time. It's doing useful processing only a small fraction of the time, as you can see. Why? Because it's stalling, basically. Now you know stalls very well, right? It's stalling because the data is not ready, because we don't have magic memory like we've assumed so far. Okay, if you're interested, you can actually read papers and other papers that are written as well. And this is an easier to read version. And this is Richard Seitz's paper. If you look over here, when we started here, I like looking at these papers and designs after 30 years or more, 40 years after they were done. And you can see that they targeted, you can see what kind of targets they wanted, basically. They wanted a long lifetime for this processor, and they said they guessed 10x of the improvements would come from CPU clock frequency, 10x from multiple instruction issue, which you know what that is right now, superscalar, and 10x from multiple processors, essentially multiple threads. But again, you can go back and read the paper saying that we're bottlenecked by memory, basically. He's saying, he starts the paper this way, but he's saying we're bottlenecked by memory, so we should really look at memory going forward. And this is more recent data from Google. This is a paper published by Google about 6 years ago. And here they essentially look at all of their data center workloads, according to them, and some spec workloads over here. And they basically show us the same thing. The red parts are where the processor is stalled. The green parts are where the processor is finishing instructions. You can see that only 10 to 20% of the time the processor is finishing instructions. Most of the time, the processor is waiting for memory. And again, you can see their analysis in the paper. It's a beautiful paper. You can see that they basically show most of the time the processor is waiting for memory. Okay, so that was the performance perspective. You may think performance perspective sounds terrible, right? We're designing, we actually put a lot of effort. This, I think, Intel Skylake, for example, this is one of the cutting edge processors of its time. We put a lot of effort into the design of these processors, computation units. And most of the time, they're waiting for data to come from memory, even though we try to optimize as much as possible, right? This, in a sense, this sucks, right? This doesn't sound good. And you've learned all of the principles, actually, right? To build very strong execution paradigms, processing paradigms. In the end, you will find out that you're bottlenecked by memory. And that's how important memory is. If you just focus on computing, and if you ignore memory, I'm not saying these machines ignored memory, but comparatively, yes, they have ignored memory. Compared to the effort that was put into the processor core, less effort was put on memory, for sure. And as a result, we have this sort of problem. And that's one thing I like about Cerebras, for example. They're basically trying to put large amounts of memory and large amounts of compute together in this wafer-scale engine, realizing that if you build a wafer-scale engine, you will have large amounts of memory as well. So it's basically people are rethinking how to design memory and compute together. And that's why we're also looking at processing in memory type of paradigms today. I'm not going to talk about that right now. Maybe if you have time at the end of the semester, we will talk about that a little bit more, because you will have a much different perspective for that. But clearly, we have this picture, even though we have the best processors perhaps at the time. Okay, if you think performance is bad, energy is actually even worse. And let's take a look at, and I think I've shown this also in one of the earlier lectures, at lecture 1 probably, but I think maybe this will resonate a little bit more with you. Basically, I have shown the slides from Bill Daly in a high-peak keynote, basically, which shows the different energy costs of different operations. And 64-bit arithmetic operation, double precision floating point. It's actually a heavy arithmetic operation, 20 picojoules based on some technology numbers. Bill Daly is the chief scientist of NVIDIA. So he has these numbers from real processors. And this is the DRAM read or write at the time, 16 nanojoules. That's 800x difference. So basically think about doing a 2 operand floating point addition, right? You need to bring 2 operands. You need to do the floating point addition or multiplication, whatever you're doing, and you need to write back the data. Basically, you need to do 3 memory accesses if your caches are not effective. We're going to talk about caches later. And that's a lot of memory access. That's basically 3 times 800x the energy of a single operation that you're trying to do. So that's a lot of energy waste. And this is shown many, many times, basically. A memory access consumes between 2 to 3 orders of magnitude the energy of a complex addition. Now, Bill Daly and some of his co-authors published another paper looking at deep neural network accelerators. And they have this nice, let's say, plot where they look at the energy of a 32-bit operation, and y-axis log scale. Now take a look at this. energy is in picojoules. A simple integer addition, not floating point, 32 bits, not 64 bits, 0.1 picojoules in some technology node. A DRAM access, 640 picojoules. So you can see there's a huge difference, right? That's 6,400. And this is written in their work. And the relative cost is basically a lot. So if you look at the relative cost, it's 6,400x. And you can see different operations over here. Multiply is, of course, more expensive over here. And SRAM cache is more expensive than a multiply. So even the SRAM cache with some size assumptions is more expensive. So basically, energy cost of memory is actually becoming intolerable, let's say. And this is a table version of that plot if you're interested in looking at the values exactly. Okay, we recently did some studies to understand the energy implications of memory access. And this is a study that we've done with Google. And we found essentially the system level implications is not so good. Basically, more than 60% of the total system energy executing the workloads that I've shown you earlier, actually, Chrome browser, TensorFlow mobile, VP9 encoding and decoding for video, average across all of those workloads, you get more than 60% energy spent on data moment. And again, this doesn't sound good, basically. We're building these computing devices, but more than 60% of the energy, total system energy spent on just moving the data around. I'm not even talking about the energy spent on storing data, for example. So computation energy is actually much lower. Okay, let me very quickly also talk about reliability and security perspectives. And I've given you some of this earlier again, but this is a study that we have done with Facebook a few years ago again. Basically, we wanted to understand the effect of the density of the memory chip on the error rates that you get on servers. And this is a correlational study done across all of the servers that Facebook has. That's a lot of servers, really hundreds of thousands, and maybe more actually. Basically, there's a strong correlation between the chip density that's used in the server. This is the DRAM chip. 4 gigabits is the highest at the time. And the server failure rate. Basically, as chip density increases, you get a higher server failure rate. Why? We get more memory errors, basically. Because memory capacity is increased. Memory cells are closer to each other because they're denser. And memory cells are also smaller, so they're more vulnerable to reliability issues and noise. And as a result, this has a huge system level impact. At the system level, you get server failures, essentially. And that affects your availability, reliability, redundancy mechanisms, etc., cost. So there are many, many implications on the systems. So, and this is a reliability problem also. And memory is a big fraction of the reliability problems today. And if you're interested, you can read the paper we wrote with Facebook about this as well. Okay, I mean, you're also familiar with RowHammer because we talked about that. So I'm not going to cover much more about that. Basically, today you can predictably induce errors in most DRAM memory chips, and this is a reliability problem because cells are interfering with each other, even though whenever you're toggling one word line, one row, you're really destroying the data in adjacent rows. I'm not going to go through this in detail again, but it's really a simple hardware failure mechanism that can create a widespread system security vulnerability. And we've also mentioned this high-level paper that talks about the gist of RowHammer, basically. It's a physical phenomenon that leads to a reliability problem that can be exploited as a security issue. And you can read our paper as well as Google Project Zero's work that talks about how to exploit these RowHammer bit flips so that you can actually gain kernel access using a user level program completely. And this is beautiful security engineering. I'm actually going to talk about this a little bit more when we get back to virtual memory, because what RowHammer does is whenever you hammer a row, you really induce bit flips in adjacent rows, physically adjacent rows, but those physically adjacent rows may belong to other applications. They may belong to the operating system. So you're really breaking the memory isolation properties of the system. And when you break memory isolation properties like this and induce predictable bit flips, someone can take over your system. Okay, so if you're interested in this, there is a lot more material, clearly. This is one thing that, one retrospective paper that we have written recently. There's more work that happened afterwards. And if you're interested, you can certainly look at the RowHammer in other lectures. And this is a lecture that I recommended because this covers almost close to the state of the art in RowHammer today, if you're interested. Okay, now that I motivated you, hopefully, at a high level, let's go into a little bit more fundamentals of memory. Okay, are there prospective alternatives to the memory cell implementations we covered, which could increase speed, like light crystal-based stuff? Certainly, there are potential emerging technologies. Actually, I'm going to end this part of the lecture with some emerging technologies. But unfortunately, many of them are slower than DRAM and SRAM. That's the unfortunate part. So speed, in terms of the latency of the cell structure, we don't really have a whole lot of materials that we know of that are faster potentially at this point. Some of them may get close. Some of them may be slightly faster, but not orders of magnitude faster. Certainly not even an order of magnitude, not even factors faster, basically. That's the unfortunate part. There are other reasons for memory technologies, as we will discuss, looking at emerging memory technologies. Reliability could be one reason. Okay, now let's jump into memory organization and technology. So far, we treated memory from a programmer's perspective, right? Basically, you have this huge memory array, and we do loads from it, and we do stores into it. And clearly, you know how to do that. That's nice. If you do it too much, you may actually destroy your performance. But before I jump into the physical organization a little bit, I should say programmer sees virtual memory. And we're going to cover virtual memory in one of the later lectures. Basically, this way, the programmer can assume the memory is infinite, or at least large enough to not worry about. In reality, physical memory size is much smaller than what the programmer assumes. The system software and the hardware cooperatively map virtual memory addresses to physical memory and don't involve the programmer in this. In other words, the system automatically manages the physical memory space transparently to the programmer to make the programmer's life easier. So the huge benefit, and this is called the virtual memory, basically. It's an indirection, virtual to physical indirection. This way, the programmer does not need to know the physical size of memory, nor do they need to manage it. And as a result, a small physical memory can appear as huge one to the programmer because the programmer isn't limited by that large size. And as a result, life is easier for the programmer. Now, that sounds great, right? And this is another example of the programmer microarchitect trade-off. The downside, of course, is more complex system software and architecture, as we will see when we cover the virtual memory lecture. And this is a classic example of the programmer microarchitect trade-off that has been extremely successful. Virtual memory has been extremely successful because it's made programmers' life easier. Now the programmer doesn't need to worry about, will my program fit in physical memory? Or will my data fit in physical memory? They don't need to worry about that. They basically write the program and the system manages if the memory overflows. Okay? So we're going to get back to this. But for now, assume that we have a physical memory system. You need a larger level of storage to manage a small amount of physical memory automatically. So there should be a backing store to main memory. And physical memory also has a backing store. It's called the disk. That's why we have disks. But we will first start with the physical memory system. And for now, we were going to ignore the virtual to physical indirection. And that's a good idea because we should really understand the underlying organization of the memory technology first. And we will get back to it later if time permits. And it looks like the time is going to permit next week or the week after. Okay, so before we go into memory organization and technology, let's have some idealism in mind. So we have three different components in a system, right? And certainly we've covered a bunch of them. Pipeline is an important one. Instruction execution. I hear some feedback. Is there some noise coming? I don't know if other people hear. I hope I'm not the one who's causing the noise, but if you can mute, that'd be great. Okay. I hope it's not from my microphone. Okay. But basically, we have this pipeline, and we have an instruction supply that supplies instructions, and we have a data supply that supplies data. And this is essentially all processing units need something like this. And we've covered a lot on the pipeline. We tried to minimize the pipeline stalls. We tried to maximize the data flow through out-of-order execution, for example. We didn't talk much about interconnect, but ideally you would like zero-cycle interconnect so that you can communicate the operands nicely. We want enough functional units so that you can exploit the parallelism. We covered this in SIMD units and GPUs, for example. And ideally, you would like zero latency compute also, right? If you really want an ideal system, you would like to achieve all of these. Okay, but we covered enough of this, so I'm not going to cover more. Instruction supply, a good chunk of it is memory, zero latency access, ideally, right? Infinite capacity, ideally, we don't need to worry about the capacity. Ideally, zero cost. And we didn't cover them. We're going to cover because instruction supply is part of memory. Also, there should be some memory over here. Perfect control flow, we try to achieve it as much as possible, right? With branch prediction lectures, for example. Okay, data supply, we have not covered a lot, basically. Zero latency. Ideally, you want zero latency access, infinite capacity, infinite bandwidth, and zero cost as well over here. So similar requirements to instruction supply, except you don't have the control flow in the data supply, right? So we're going to talk about this clearly. We're going to try to think about the ideal, especially in the second part of this lecture. But let me, actually, this is a good place to probably take a 10-minute break. It's a good lecture break point. After that, we will start with an overview of the memory arrays and then talk about memory technology. And then we'll build up to the memory hierarchy. So let's take a 10-minute break, be back at 15:10, and then we will continue. Okay, let's continue after the break. So now that we have a good overview of why memory is really important and what idealism means, we're going to get back to this idealism. Let's start with a ground-up view of memory arrays and what they look like. You've actually seen this before, so some of this is going to be reviewed. I hear myself from here for some reason. Okay, that's much better that I don't review myself, hear myself. Okay, so this in the end boils down to how do we store data? And there are different ways of storing data, some of which we have seen. And we're going to build arrays from each of these data storage elements. So if you look at memory, memory consists of arrays of arrays of arrays, essentially. And we will see why that's the case. But in the end, it all starts with a single data storage element. And that data storage element could be a flip-flop or latch, as we discussed, or static RAM, dynamic RAM, static random access memory, dynamic random access memory, or some other storage technology. We will, at the very end, look at phase change memory very briefly, for example. It could be hard disk, some magnetic technology, tape, flash memory. Essentially, in the end, these are all, dictate the storage technology. And in the end, you have a storage device that stores the data. And then you build an access device around it to access the data. And then you build arrays of these cells. And that's why we're going to focus on arrays. So if you look at any memory type or any storage type, it may look similar because it consists of arrays of cells, essentially. Okay, just to remind you, flip-flops or latches, we covered them in the sequential logic, and then we use them in many of our labs. The big advantage here is they're really logic-based, right? And they're very fast. They can give you parallel access, but they're actually very expensive, very costly. And usually cost is in terms of area cost in memory. How many bits you can pack in a given, let's say, millimeter square. That's we will see that actually in the next part of this lecture. But 1 bit costs tens of transistors. If you remember, we did some very rough calculation in D flip-flop, and we said there are more than 40 transistors inside this D flip-flop, right? That's a lot. Static RAM, we will describe it in a moment. You've actually seen it. This is a cross-coupled inverter, and then we have some access transistors. It's relatively fast. You get only one data word at a time, but it's expensive. 1 bit costs 6+ transistors, as we will see. It's usually 8+ transistors if you include the access transistors. Dynamic RAM, we will describe also this later in this lecture, but it's slower. Reading destroys content, as we discussed, refresh at the very beginning of the lectures, right? Lecture 1 or 1, 2, 3. And needs special process for manufacturing because it's capacitor based, but it's cheap. 1 bit costs only 1 transistor plus 1 capacitor. So that's why we build off-chip main memories using dynamic RAM. Static RAM is compatible with logic, and it's relatively fast. That's why we put it inside our processor computation units, close to computation units. Dynamic RAM, on the other hand, it's not compatible. The manufacturing technology of dynamic random access memory is not compatible with the logic technology, at least not efficiently compatible, I should say. If you want to pack many, many capacitors in a chip, you need to actually have a different process, manufacturing process. As a result, we have separate chips for dynamic RAM. And as a result, we have processor chip and memory chip, main memory chip. And the reason dynamic RAM can be main memory is because it's cheap, basically. It's much cheaper than this expensive static RAM. You can also make your static RAM main memory, but it turns out it's very expensive, as you can see. Okay, and there are other storage technologies that we're not really going to cover in full, but this hierarchy actually continues. These are much slower, access takes a long time, but the big advantage of these technologies are they're non-volatile. So whenever you plug the power off, whenever you turn off the power, they can retain data inside them for years. As a result, they're good for long-term storage as opposed to short-term working memory, right? But, and also, they're also very, very cheap. Here in flash memory, for example, today, 1 transistor, it's a special type of transistor. It's called floating gate, for example, transistor. And that can store many bits. It can store 16 bits at a time, for example, in the most cutting edge technologies. And there, in some technologies, there are no transistors involved because there are magnetic storage, for example. And we're not going to go into that. But this is clearly fascinating. And if you're interested in all of this, I would recommend you take the master's level computer architecture course, which goes into memory in much more detail. Okay, but these are the storage elements, essentially. And we build arrays of these storage elements. And essentially, all memories, maybe except for some of the tape type of memories, for example, all main memory technologies, flash memory type of technologies, and SRAM technologies, in order to efficiently store large amounts of data, we organize these cells into arrays. And arrays you've already seen. I'm going to show you the examples that you've seen soon. But basically, you have a memory array, and you have which stores data. This is a two-dimensional array of cells, essentially. And we have some address selection logic. In fact, actually, I should probably say that there was a comment on three-dimensional technologies, right? Flash memory today, for example, has gone three-dimensional. So in flash memory arrays, today we have actually three-dimensional arrays. You can call them cubes, perhaps, right? Not necessarily arrays, but essentially three-dimensional technologies. Whenever you can actually build three-dimensional technologies, then you can actually get more density with those technologies. So keep that in mind as well. Array is two-dimensional because we are able to comfortably build two-dimensional technologies today on the logic processes and manufacturing technologies we have. But if you could go three-dimensional, certainly that's a possibility, right? And if you're interested, I recommend looking into our flash memory lectures from the computer architecture course, which talk about some of these three-dimensional technologies. Okay, but let's restrict ourselves to two-dimensional technologies right now. In two-dimensional technologies, basically, we have a memory array, two-dimensional array of cells that store data. We have address selection logic, which selects one row of the array. Basically, you first access the row, you give the row address, and then you also give a column address to get the data out if you actually are supposed to select from a column. Okay. In some cases, you may not need to select from a column in this particular example that I'm going to give you. But in DRAM, for example, you need to select from a column. And then you need to have this readout circuitry that reads the data out, essentially. Okay. So in this particular case, an m-bit value can be read or written at each unique n-bit address over here. All values can be accessed, but only m-bits at a time here. So even though you may actually be storing huge gigabytes and gigabytes, you write and read only m-bits at a time. Okay. And access restriction allows more compact organization in the end, basically, because you're not able to access everything at the same time, because that requires huge porting, clearly. Okay, recall we've already done this actually. We exactly had an array that looks like this. Here, this is lecture 6 and 7. This is the bigger memory array we've seen over there. We had 4 rows here, 4 word lines, if you will, and an address decoder, and then 3 bits stored in each word line, right, in each row. And in this case, we read 3 bits, but you could also have another multiplexer that selects 1 bit at a time. Basically, you could actually have 4 rows, and you could read only 1 bit at a time, right, if you had another multiplexer at the bottom, right? Here, in this case, we read 3 bits. Okay, so this is a 12-bit memory array in total. And this is another example of it, basically. Here, I've actually shown you the 12-bit memory array over here as an example. Essentially, all memory arrays are a two-dimensional array of bit cells. Each bit cell stores 1 bit, and we already know what a bit cell looks like. In this case, this is a latch, as you can see over here. And an array with n address bits and m data bits has to the n rows and m columns. You can think of this as depth and width also. Depth is the number of rows, and width is the number of columns. Column is the side of word, and depth is the number of words. Don't get too stuck on the terminology. It's basically rows and columns in the end. And the array size is really the multiplication of the depth and width to the n times m. And you can see an example over here to the 2 times 3, which is also the example in the previous thing. Okay, basically, this is the example that we've seen. I'm not going to go through this again because you already built these memory arrays. You know the register files. Register files look like this also, except they're bigger. But basically, you can get the 3-bit word stored address 10 over here just by looking at what's depicted. Okay, so here I should say that the row size is only 3 bits, right? But your row size in DRAM, for example, can be 8 kilobytes. So you may, for example, have number of rows, 16,000 rows, and 8 kilobytes row size in each row. Okay, but your data out may still be only 64 bits, for example. You may get only 64 bits out of that 8 kilobyte row, or 64 bytes out of that 8 kilobyte row. Basically, you select or you multiplex the data, the column that you want out of that memory. Why is the array organized this way? So that you can pack together many cells at the same time, right?
if you have an array that's like 16,000 rows and only 64 bits, let's say, in each row, your density is lower, basically. People have found out that more or less rectangular arrays give you good density. Of course, today's DRAM technologies are more complicated than that, but this is a good first order approximation. If you have a more or less rectangular array, 16,000 rows and 8 kilobytes row size, then you pack enough bits over there so that you maximize the bits per millimeter square, let's say. That's how array size is usually determined. But that's not the only factor. We will talk about another factor, which is latency. Because as your array becomes bigger, your interconnect word lines and bit lines also become longer. So you don't want to make your array size too large. So you actually have a smaller array and then replicate those arrays and then build bigger virtual arrays, let's say, or logical arrays out of these smaller physical arrays. Okay, but internally, a physical array or virtual array is usually rectangular, and it's not just 3 bits. 3 bits is too small to make it cost effective. You usually have thousands of bits, for example. Okay, keep that in mind. As a result, because you don't read thousands of bits, you read literally 64 bits or so, because otherwise you'll have huge interconnects. And especially if you're reading off chip, then you need to be very careful, because whenever you're reading off chip, you need to have pins to go out of the chip. And those pins are extremely costly. And you may not even have thousands of them, because they occupy a lot of area. Your chip may not be able to accommodate thousands of pins. As a result, your data width is usually small, let's say 64 bits, for example, or 8 bits. So as a result, if your array row size is 8 kilobytes, you need to select the 64 bits from your column, from the appropriate column based on a column address. So we will see this in a little bit also, but this is important to keep in mind. That's why we size the arrays to maximize capacity to while getting acceptable latency. Okay, this is a larger and wider memory array. You can see that this is 1024 word and 32 bits. And you can clearly make this bigger and bigger. You can make it 1024 by 1024, etc. And you can increase the size. I'm going to give you the sizes from modern DRAM chips soon. Okay, let me give you some more terminology. So now you know the array organization clearly. You've seen it before also. But these are storage nodes, let's say, or storage cells. And storage cells in one column are connected to one bit line. You can see the bit line 0 over here, for example, that is connected to this column, these store bits over here. And then bit line 1 is connected to this column, and bit line 2 is connected to this column. So basically, you have bit lines running on the y-axis, getting each bit out, and you have word lines running on the x-axis to decide which row of cells should be activated. Essentially, address decoder gets a 2-bit address over here and activates one of the word lines, because we have 4 rows, right, in this case. And for example, if the address is 10, the activated word line will be 2. And the content of the entire word line will be activated. And what will happen is the stored bit will be sensed through the bit line in some way. We will see partially how it's done in some technologies. And the data gets out, basically. And that happens concurrently. So if this word line gets activated, so this stored bit essentially is read through this bit line. This stored bit also is read through this bit line, and this stored bit also read through its bit line. So you can read concurrently 3 bits at the same time in this particular case. And we've seen it also, right, earlier with the example that I've showed you again. And in the end, content of one line of storage or one row of storage is available at the output. Okay, so hopefully this is clear. And this is, I've already given you this example, basically. If you activate word line 10, you get data 100 out. And again, as I said, if this is too large, if 3 bits is too large, you can multiplex only 1 bit, right? If all you care about is getting 1 bit out, and if your outside interface outside of the chip is only 1 bit, basically you can multiplex out one of these bits based on the column address that you care about. Okay, so how is access controlled? Access is controlled by access transistors, essentially. And these are configured as switches. And these connect the bit storage to the bit line. And you can see that, basically. And access transistors are controlled by the word line. So let's take a look. So basically, you can imagine all technologies as stored bits. And stored bits is controlled by the word line. And word line, once word line activates the row the stored bit is on, the stored bit is sensed using this bit line. And as a result, you read the value of it. And in a word line, there are many stored bits, and there are many bit lines as a result of this. Okay, so DRAM, for example, stores data in a capacitor over here, but the access circuitry is this access transistor. So if the word line is enabled, the access transistor enabled, and the capacitor shares charge with the bit line, and there's some sensing circuitry, sense amplifier at the bottom, that detects that charge perturbation, charge sharing, and figures out whether the capacitor is charged or discharged. As a result, you get you can encode a value 1 or 0 in the charge state or discharge state. It's so simple, basically. You need to activate the word line to get the data out. That's true in SRAM also. You need to activate the word line to get the data out from this cross-coupled inverter. Sensing is a little bit different. It's dependent on the technology, basically. So you can see that the storage unit is a capacitor in DRAM. In SRAM, the storage unit is a cross-coupled inverter. And you know what this is before because we've seen them actually, right? You can see that the access transistors in this case are 2 of them. One of them reads the positive value, and the other reads the complement of the value. One of them reads the stored value, and the other reads the complement of the stored value. Clearly, that's what you do in a cross-coupled inverter, right? Here you have the stored value. Here you have the complement of the stored value. Now you have 2 bit lines in this particular SRAM implementation, a bit line and a bit line bar. And there's some sensing circuitry at the bottom over here that does differential sensing of the bit line so that you can get more robust reading. So you basically sense the difference between the bit lines, and having one bit line as the highly charged and the other one, the opposite charged, amplifies, makes it faster to do the sensing essentially. That's why you look at bit line and bit line bar. But this is one example of reading circuitry. You can certainly build SRAMs where you just look at bit line or bit line bar, basically. This is more expensive, if you will, and maybe more stable when you reduce the size of the SRAM to smaller sizes. But essentially, you can see now that we can abstract both of them like this. They both have a stored bit. They both have a word line and bit line. And I don't care what's inside the stored bit, maybe, right? That's the abstraction level, if you will. But if you go inside the stored bit, it looks different, as you can see. So DRAM is just one capacitor. SRAM, you can see that it's 2 cross-coupled inverters, and you know now that it's 4 transistors. So now you have 4 transistors and 2 access transistors over here. So you have 6 transistors in SRAM, whereas 1 transistor and 1 capacitor in DRAM. So DRAM is going to be cheap because, or less costly, less area cost, because it stores data in a more frugal way, in a smaller capacitor, as you can see. Okay, and this is going to be one important distinction between DRAM and SRAM. So we can pack many more gigabits per square millimeter over here. So there's one question about why would you use memory to perform logic if memory is so energy and time intensive? Well, that's a good question. I think it's already partially answered, because FPGAs, you want it to be programmable. But also smaller amounts of memory may not be as intensive, right? So if you actually have smaller memories, if you do lookup tables in huge gigabytes, maybe that's going to be energy intensive. But if you have smaller memories, it's not going to be as energy intensive, right? That's what the numbers showed actually. If you have smaller SRAM, the energy costs are much lower. Also, there may be other trade-offs, but I'm not going to get into it right now. If it eliminates, if you're using lookup tables to do computation, eliminates data movement to do computation on a processor or an accelerator, then it may actually be a net gain actually. Okay, very good questions though. Okay. So now building larger memories. Now I'm giving you a single bit over here also, but you build an array of these bits, and building larger memories requires larger memory arrays, clearly, right? If you want higher capacity, which we do, I hope I motivated you with the real workloads, you need larger memory arrays. Unfortunately, there's this fundamental thing that says large is slow fundamentally, and that's true. Otherwise, it's magic, basically. That's very fundamental. So the question is, of course, how do we make the memory large without making it too slow? And that brings us to the hierarchical structure of modern memories, basically. You don't remember this view that I showed you. It's a huge memory array, right? You may have a 4 gigabyte memory. It's from a programmer's perspective, it's a huge memory array. But internally, physically, it's an array of arrays, basically. Internally, you have many smaller arrays that make up larger logical arrays that may make up larger logic arrays as well. And we will see that in a little bit. But basically, this is so to answer this question, how do we make the memory large without making it too slow? We have actually seen this idea a little bit. Divide the memory into smaller arrays and interconnect the arrays to input and output buses. That's the idea. Large memories are hierarchical array structures. And DRAM, particularly DRAM we're going to look at in a little bit, has a 5-dimensional structure, maybe even more today. I don't quote me on the 5-dimensional exactly, but channel, rank, bank, subarrays, mats. We will see another example of it. But we've already seen the concept of banking, for example. Remember, the general principle is really banking. And we've seen banking from a different perspective, but I've also mentioned this aspect of it when we talked about SIMD processors, right? We want high throughput, 1 word per cycle in a vector processor. In a GPU, we want even more. So why don't we bank the memory such that we can start 1 access per cycle in each bank concurrently? So let me, our goal was to get one word per cycle throughput. So banking certainly helps throughput as well. But it also helps this. Well, this actually has throughput in it as well. Basically, if you have a single monolithic large memory array, if you look at memory from the programmer's perspective, a single monolithic large memory array, you do a load and store, and you get 1 result at a time. You cannot make it too large, or if you make it too large, it becomes too slow. Essentially, if that large memory array takes too long to access, that's one problem with it. Another problem with a huge monolithic memory array is that it doesn't enable multiple access in parallel unless you have multiple ports to it. Multiple ports are expensive, as we discussed. So I'm going to not assume multiple ports here. But basically, a huge, large physical monolithic memory array has 2 problems. It takes too long to access because the interconnects are long, both the word lines and the bit lines. And you cannot do multiple access in parallel. So how do we fix this? Well, we want to reduce the latency of a memory array access and also enable multiple access in parallel. And the idea of banking actually gives you both of these at the same time. And banking at a higher level really divides the large array into multiple banks that can be accessed independently, either in the same cycle or in consecutive cycles. In the vector processor example, we saw consecutive cycles. But in some on-chip banks, for example, SRAM banks, you may actually access the different banks in the same cycle concurrently at the same time, basically. So that's the basic idea. I mean, you've seen the basic idea. Each bank is much smaller than the entire memory storage. And now accesses to different banks can be overlapped. Because each bank is smaller than the entire memory storage, latency is lower because interconnects are much shorter to access. And you have concurrency in access. So your throughput is also high in this case. Concurrency means throughput in the end. And then, of course, we already discussed this in the SIMD processors as well as GPUs a little bit. How do you map data to different banks becomes a problem. How do you interleave data across banks becomes a problem. I'm not going to talk about that. But if you want to ensure that your latency and throughput are high, you want to ensure that your concurrent memory accesses go to different banks, right? If they go to the same bank, then one of them needs to wait for the other, because assuming banks are not multi-ported. But if you map your data nicely, your accesses will go to different banks, and you will get low latency and high throughput at the same time. That's why this banking mapping of data is extremely important. And we discussed in the SIMD processing lecture. And I also pointed you to a beautiful paper by Bob Rao talking about pseudo-randomly interleaved memory so that you can minimize these bank conflicts. I'm not going to talk about that in more detail. And this is just for your recall, if you will. This is how we introduced memory banking, right? Memory is divided into banks that can be accessed independently. Banks share address and data buses to minimize the ping cost in DRAM. This is the DRAM perspective. But if you have an SRAM that's on chip with the processing elements, this may not be a constraint, right? Basically, you don't go off chip. You don't go through the pins to access memory, SRAM. As a result, you can actually have banks that have separate data and address buses, and you can start and complete all access at the concurrent. But in DRAM, as we discussed in the SIMD lecture, you can start and complete 1 bank access per cycle, and it can sustain n concurrent access if all n go to different banks. And we said basically, if your memory access latency is 11 cycles, you need 16 banks to ensure that you can get 1 word per cycle throughput. But of course, this is true if your memory accesses go to different banks, right? Okay, there's one question. So is a certain part of memory reachable only by a certain bank, or is this assigned dynamically? I don't quite understand the question here. So all of the memory is reachable by by supplying the bank address row address and the column address, right? So the memory controller needs to supply which bank you're accessing. And each bank has a partition of the memory, basically. Our register is usually SRAM. That's a good question, basically. Registers could be SRAM, yes. Registers could be flip-flops also, potentially, if you want to make it really fast or for some reason. So either SRAM or flip-flops. Don't we also need ports to access banks? Isn't it expensive as well? Yeah, certainly you need ports to access banks, but that's no real different from having a single monolithic array. A single monolithic array has to have ports, and each bank has to have a port also. You're just basically partitioning the single monolithic array into banks. Okay, so for example, if is memory address 1 through 124 unreachable by bank? Yeah, absolutely. Basically, you imagine this as so basically, let's say you have 16 gigabytes of memory. I just made it up, and you're dividing it into 16 banks. What do? You basically have 1 gigabyte banks, and clearly physical memory addresses that go from, let's say, that are within the first gigabyte are within bank 0. The physical memory addresses that are between 1 to 2 gigabytes are in bank 1, and etc. Right? It depends on how you do the address mapping, as we discussed in the SIMD processors lecture. But these are partitions, basically. Okay, good. Okay. So let me give you the generalized memory structure a little bit. So this hierarchical memory structure, looking at DRAM. And I'm going to look at this is the memory controller, and this is the memory channel. I'm going to give you a pictorial view of it also. But let's start with the bottom over here. So the bottom is two-dimensional array, and we're going to start with banks as the smallest physical two-dimensional array. And you can see that a bank consists of two-dimensional array of cells, and it can have many rows and many columns. And a cache line could be 4 of these columns, let's say. This picture just makes it up. And a single DRAM chip may be 4 banks, as you can see over here. And a DRAM module may have 4 ranks. So I'm not going to go into the details of 4 ranks right now, but you're going to see a picture of it later on. But ranks are the DRAM. The goal is to minimize the cost as much as possible while not destroying the latencies, let's say. As a result, the DRAM chip is small. And if you want to build larger memories that are higher throughput, you put them together as 4 of these chips, for example, and they form a rank. A rank of chips respond to the same command at the same time. So if each of these chips, for example, supply 64 bits, 4 of these chips concurrently supply 4 times 64 bits to you. That way you can get higher throughput as well as higher capacity at the same time. That's the concept of a rank. Now, this is a module also. So you have 4 modules in this channel, 4 modules in this channel. So you have multiple channels also, so that you can again both improve throughput. You can do multiple accesses. And you can also have higher capacity, as you can see, right? So this hierarchical structure enables you to start with a low access latency as much as possible and build up to high capacity as well as high bandwidth at the same time. So this hierarchical structure is really an interesting science plus art design to maximize, reduce latency as much as possible, maximize capacity, minimize cost, and also get as high bandwidth as possible. So you can see implications of the structure on all the 3 metrics: cost, meaning capacity, latency, as well as bandwidth or concurrence. Okay, that's one example. This is another example from one of our papers. If you're interested in looking at it, this is a cleaner potentially example. It depicts essentially the same thing, basically. Okay, now let me give you a top-down view of the DRAM subsystem, just to give you a real idea of what DRAM looks like. SRAM looks very different. It's internally hierarchical, but DRAM is a bit more complicated because it's its own subsystem. Let's see how this looks. So as I said, DRAM has a hierarchical organization. We start with a channel, and then we have a module. Each module is composed of ranks. Each rank is composed of chips. Each chip is composed of banks. And then each bank is a 2-dimensional structure, rows and columns internally. Okay, so this may be a processor that you may have. Actually, many systems, there's nothing special about Intel over here. All systems look kind of like this. So they have multiple memory channels. In fact, more recent Intel processors may have 4 or more memory channels. But basically, you have memory channels so that you can access 2 different things at a time, right? That's one thing, concurrency. And also, you may add more memory modules on each channel. That way, you get more capacity, basically. So this looks like a real system with each channel having 2 modules. Just made it up, right? A module is also called dual inline memory module in systems. You don't need to exactly know what that means. Just think of it as a module. But this is something that you plug into your motherboard, for example, right? Okay, now let's dig deeper a little bit. Let's dig deeper and look at this module. So you can see that the module consists of chips, right? And there's a front and back. It depends on how the module is constructed. There's a programmable chip over here also that the memory controller reads to understand what kind of memory it's dealing with. We're not going to go into that. But you can see that the module has 8 chips in this case, and on both the back side and the front side. And again, there's a reason for it. Why do you have both backside and front side? Backside is a rank, front side is another rank, actually. And the reason is, again, to maximize concurrency. You can have concurrent access to different ranks, and also maximize capacity. You get higher capacity as well. And again, these are not monolithic arrays. You don't have a huge chip. You have many chips, as you can see. As a result, you also reduce latency as much as possible. So again, rank 0 is a collection of 8 chips over here, and rank 1 is the back of the DIMM, another collection of 8 chips, basically. Now let's take a look at each rank. So each rank actually gets address and command buses. They're shared because pins are costly, as I said. That's why there's a lot of sharing of the address and command buses, and data bus also, as you can see. Ranks actually supply. So you cannot access 2 ranks concurrently at the same time, just like you cannot access 2 banks completely concurrently. But you can access concurrently, but you cannot get data out of them in the same cycle because they share the data bus, as you can see. So you select which rank to access based on the memory address. There's a chip select signal that's part of your memory address. And then you get 64 bits of data out. And you also need to supply other addresses, as we will see, like the row address and the column address. But this is your memory channel, basically. Memory channel actually has 2 ranks from one module. Okay, if you break down a rank, what you see is what I kind of showed you earlier. You have multiple chips, in this case, 8 chips. And each chip, so whenever you do an access, you get 64 bits of data out. And each chip supplies only 8 bits of it. Why? Because chips are very much cost constrained. So you minimize the cost by minimizing the number of pins. And pins are cost, essentially. So if you want to minimize the cost of a chip, you have only 8 bits outputs. How do you get higher bandwidth? How do you actually construct 64-bit output? Now, basically, you put eight of these chips together, and you operate them as a rank concurrently. It's like a rank of soldiers. You give the same command to everyone, and every chip responds with different data, essentially. That's how you can actually increase the bandwidth of a chip that is a narrow data bus, as you can see, a small number of pins. Okay, we get 64 bits out over here. Nice. That also increases your capacity, actually, because now you're putting many chips at the same time. So you get both bandwidth and capacity. Okay, if you go into the chip, now the chip looks like 8 banks, as we have seen earlier, right? And each bank, again, shares address, data, and command buses. As a result, you can start 1 access per cycle in different banks, and you can get 8 bits per cycle from a different bank. So you get concurrency at multiple levels, as you can see, rank level concurrency as well as bank level concurrency. This is the bank level concurrency part. And now if you break down the bank, you're back to the picture that I showed you very early in one of the earlier lectures when we looked at memory performance attacks, for example. Basically, you have a 2-dimensional array of cells. You have rows and columns. And you see that here we have 32,000 rows and 2 kilobytes row size. Each column is 1 byte over here. And you can see that we activate 1 row, bring it into the row buffer. And then to get 8 bits out of them, we select the column based on the column address. So you need to supply the row address and the column address over here so that you can get the data out appropriately, of course. So now we're back to the memory array structure. This is the memory array structure, basically. This is the 2-dimensional array that we discussed earlier with a very small memory, 2 to the 2 by 3, right? Here, it's really 32,000 rows. Each row is 2 kilobytes. And then the data out is only 8 bits, as you can see. And this is our bank. Okay, now we're not done. This is the abstraction of a bank, actually. Internally, there are arrays inside it also. This is the abstraction that we have as a memory controller. Why is it abstraction? Even this is too big, too large for this. If you have 32,000 rows, essentially your bit lines are 32,000 long, right? Your word lines are also long, 2 kilobytes in this case. And that's too slow, basically. Your interconnects are too long. In order to make it faster, people actually break it down into smaller subarrays. So internally, a DRAM bank actually has sub-banks. And this is the array inside array kind of structure that I mentioned. But these are not visible to the memory controller currently. In the future, I hope they will be. But essentially think of this as reducing the latency of the memory array while building bigger arrays. Okay, and if you're interested, you can read these works. And this is another view of it. This is a more detailed view. And basically, this is a bank, a view of a DRAM bank over here. This is a logical abstraction. Physical view is it really consists of sub-banks, each of which actually consists of mats internally. So even the subarray is an abstraction over here because you can break down the subarray into mats also, basically. So this is logical abstraction, physical implementation, but even this is an abstraction because subarray internally has mats as well. Again, why? Because the wires are too long. Too long wires means too slow access. So you break it down into smaller arrays. So hopefully this gave you an idea of memory arrays. And I think I liken this to snowflakes, not exactly maybe, but whenever you focus into a snowflake, you see snowflakes. Whenever you focus into a memory array, you see memory arrays internally. And you keep seeing memory arrays. In the end, you end up with a cell. Okay, so if you're interested in DRAM basics and organization, actually, there are not a lot of easy to access material related to it. But in this book chapter, we try to do a good job building from a transistor and capacitor, and then giving you the full array structure. And this picture is actually from that book chapter, and you can take a look. Okay, so let's take a look at how you transfer a cache block. We're going to talk about caches very soon in the next lecture. I'm going to introduce the idea of memory hierarchy toward the end of this lecture. But let's take a look at how we read the cache block from a top-down perspective in this picture that I've shown you, just so that you understand what's going on and what will go on. So basically, physical memory space looks like this. It's huge, as you can see. And a 64-byte cache block gets mapped to some memory, essentially physical memory address. And this gets mapped to a channel and a rank and a DIMM, basically. A cache block doesn't get distributed across channels. It normally gets mapped to a channel and a rank and a DIMM so that you can read the entire cache block from one single memory module. And you can read another cache block from another memory module in some other channel, for example, absolutely concurrently. Okay, so how do you read a cache block, basically? This is our module, right? Module consists of 8 chips in this rank. And basically, cache block gets distributed across these different chips to the same bank. So bank 0, let's say, to different chips. And different chips respond with different pieces of the cache block. So this is row 0, column 0 in bank 0, let's say. And you read it from all of the chips, and each chip gives you 8 bits. So you get 64 bits out, okay? 64 bits, that's nice, but our cache block, as I said, is 64 bytes. So what do? You read the next 8 bytes after you read the first 8 bytes. So you keep reading 8 bytes from consecutive locations to get 8 bytes, meaning 64 bytes in the end. Which means that a 64-byte cache block actually takes 8 I/O cycles to transfer. And during the process, 8 columns, each of which is 8 bits in each chip, are read sequentially. And 8 chips are involved, basically. Okay? So basically, each chip provides 8 bits. Concurrently, 8 chips provide 64 bits in one cycle, I/O cycle, bus cycle here. And then 8 consecutive cycles provides 64 bits per cycle. As a result, you get 64 bytes of a cache block out. Okay, so hopefully this is going to be useful in the later lectures. And this is one of the reasons why memory access takes longer, basically. You need to, even just for 64-byte access to memory, you need to use 8 cycles. And you also, of course, you need to activate the array, etc. And it takes some time. Okay, now let's focus on memory technology in the remaining parts. And this will lead us to memory hierarchy as well. Actually, there's one question. So if so many memory locations are concurrently accessed, wouldn't a RowHammer attack change a lot of positions as well? So I'm not sure I completely understand the question. But basically, a RowHammer attack happens when you access one single row many times. So if you're accessing some other rows in some other chip, then that's not going to affect your RowHammer attack. Okay, if you have other questions, please write it. Okay, so memory technology. We already discussed DRAM and SRAM, but I'm going to go into a little bit more detail and then introduce phase change memory as well. So DRAM clearly is one of the cheapest main memory technologies. Capacitor charge state indicates stored value. Whether the capacitor is charged or discharged indicates storage of 1 or 0. You can encode it either way. And essentially, your storage device is very simple. It's just one capacitor. That's why this is very dense and low cost. But you need an access transistor to enable access to the capacitor. That's why it's called row enable over here, but it's nothing different from a word line here. Okay. So the one disadvantage of DRAM technology that we discussed is refresh. Capacitor leaks its charge through this RC path, resistance conductance path. And as a result, DRAM cell loses charge over time, and it needs to be refreshed. Okay. And we talked about the implications of this in one of the first lectures, and you can go back to it as one of the mysteries that we discussed, right? Static random access to memory doesn't have that refresh problem. It has two cross-coupled inverters, which we discussed earlier, actually. And there's a feedback to store single bit. Feedback path enables the stored value to kind of persist in the cell while it's powered on. So you have 4 transistors for storage. That's nice, but you need to have 2 transistors for access. As I said, you could make it 1 potentially, but in scale technology, that becomes difficult to sense. So you have row enabled transistors as well, access transistors. As I said, both memories have a memory bank organization, right? You have a 2-dimensional storage array, and the memory bank organization looks like this. You have an address that gets lashed into the address register. Most significant bits are used for figuring out what is the row. Again, these are dependent on how you do the data mapping, but usually the most significant bits in the address are used to determine which row you're accessing, and least significant bits are used to determine which column you're accessing. So it may be 26 bits, for example, and 13 bits are here and 13 bits are here. I just made it up again. But basically, once the row decoder decodes the word line gets activated, and the entire row is read. And then least significant bits are used to multiplex out the data, the column that you're really looking for. So read access sequence, you decode the row address and drive the word lines. The word line that you are really accessing using the address is activated. The selected bits drive the bit lines. So you do an entire row read. And then you amplify the row data so that you can sense the data inside. And each memory technology has different sensing mechanisms, as we discussed. Then the column decoder decodes the column address, these least significant bits, and select the subaddress of the row and sends it to the output. So it's very simple. Most memories look like this in the end. And then, of course, now you've done one access to this array. If you want to start another access to the array, you need to pre-charge the bit lines so that you can prepare them for the next access. So there's one question. So data out is usually 1 byte. It depends, basically. It depends on the DRAM chip. It depends on the SRAM. So in DRAM chips, it could be 1 byte. It could be 16 bits. It could be 32 bits. It could be 4 bits also. There are some DRAM chips that are that way. But in SRAM, it could be actually much more wider, because in SRAM, you normally put SRAM on chip. And on chip, you don't have a pin bandwidth, pin number problem, pin count problem. Okay, so you need to pre-charge the bit lines for the next access so that you can do the sensing well in the next access. So remember, in DRAM, for example, you need to sense the charge in the capacitor. So your bit line needs to be stabilized to some value so that you can sense it well. If you don't stabilize it to some value, to some intermediate value so that you can sense the perturbation, then you may not be able to read the data correctly. That's why you need this last step, pre-charging the bit lines for the next access. Okay, so static random access memory. Essentially, it's the same, basically. I'm going to go through these relatively quickly. As I said, n is usually equal to m to minimize overall latency and maximize the density. So you basically supply n plus m bits. N of them go to row address, m of m go to column address. And these are on chip usually. So you supply all of the address at the same time, usually, because SRAM is on chip. And read sequences decode row select, which is the word line drive. You select the bit lines drive the bit lines, the entire row is read together. And then you do differential sensing and you select the column over here at the multiplexer, and the data is ready. And to prepare the array for the next access, you pre-charge all bit lines to a known value so that you can do the sensing well. So access latency is usually dominated by driving the word lines and driving the bit lines, steps 2 and 3, basically, as expected, because these are long interconnects. So whenever you're driving long interconnects, you have long access latency. And cycling time, which is how fast you can access the next how fast you can start the next access, that's called the cycling time, is dominated by steps 2, 3, and 5, usually, which is 5, because you need to pre-charge all bit lines, which also is proportional to the length of your bit lines. Basically, the operations that are on your critical path that manipulate long interconnects are on the critical path of your next access, which is word line driving, bit line driving, and then the bit line pre-charging. That's why this is there. And you can imagine what each of these is proportional to. These are proportional to the length of the wires that you're driving, essentially. Okay. Dynamic random access memory is very similar, as you can see. except normally you don't supply the row address and the column address at the same time. Why? Because you have limited pins in DRAM chip. So DRAM chips try to minimize the number of pins that you need to drive, that you need to have. As a result, they don't want you to give both the entire address at the same time. You give the bank address, you give the row address, and then you give the column address. That's the idea, basically, so that you can minimize the pin count. But the rest is very similar, actually, except for the sensing, of course, right? As you know, bit is stored as charge on the capacitor, and when you read, bit cell loses charge, and bit cell also loses charge over time because of the capacitive storage. But read sequence is the same as SRAM. You decode the address, activate the word line, drive the word line, and then drive the bit line, and then do the sense amplification. There should be some sense amplification circuitry that's we are not going to discuss in detail, and the data gets multiplexed out in the end. And then you pre-charge all bit lines again. So reads are destructive. That's one major difference between DRAM and SRAM. Whenever you do reads in DRAM, you destroy the entire row of data because the capacitor lose their charge because they share their charge with the bit line. And as a result, you need to replenish. You need to write back the data into the capacitors, basically. And also, there's another reason why you need to refresh. You lose charge over time, even if you're not reading these capacitors, because capacitors leak. So at the end of this pre-charging, actually, at the end of this reading, there's some circuitry that ensures that the data gets restored into the cells, which we're not going to talk about. But periodically, you also need to refresh the entire DRAM array so that you don't lose data over time. And we discussed this. If you want to go back to lectures 2 and 3, for example, we discussed DRAM refresh, and you can refresh your memory about this. No pun intended with refreshing your memory. But basically, a DRAM controller must refresh all of the data in all of the DRAM chips every 64 or 32 milliseconds, sometimes every 16 milliseconds at high temperatures today. And that's unfortunate, as you can see, and that leads to energy and performance overheads. Okay, now let's compare DRAM and SRAM quickly on this slide. And let's look at DRAM. The SRAM part is really the opposite of what we see over here. DRAM is slower access. SRAM is faster access. Capacitors involved. As a result, DRAM is slower. And there are multiple reasons. DRAM actually can be made faster, but not as fast as SRAM. DRAM is higher density. Clearly, one transistor, one capacitor. SRAM is lower density. DRAM is lower cost because of the higher density. You can pack many, many cells in a given millimeter. As a result, the cost is lower, as we will see in the next lecture. So these are positives, clearly, while slower access is not a positive. But the downsides of DRAM, other than slower access, it requires refresh, which affects power, performance, circuitry, entire system. And also, manufacturing requires putting capacitor and logic together. That's why we cannot manufacture DRAM, at least to at the same good levels of density on chip, where we build the processors as well. That's why we need a separate chip for DRAM. But it has a lot of advantages. Even though it has all these disadvantages, it has this density and cost advantage, which makes it a really important technology today. And it's faster than some other technologies like SSDs, clearly, right? Very, very comparing DRAM and SRAM, which are two technologies that we're going to use a lot in the remaining part of these lectures. Okay, so keep this in mind. This is important. Now, you can do this for any technology. Now, in the remaining time, let me quickly introduce you to some other technology that is actually happening right now. This is phase change memory. It's, as you can see, it has a similar cell structure of array structure, word line and bit lines, but the storage element is very different. So basically, it stores data in phase change material. And one example of phase change material is chalcogenide glass. It exists in two states, amorphous and crystalline. And the way you read data out of this is really interesting. Basically, amorphous state has low optical reflexivity and high electrical resistivity. And crystalline state has high optical reflexivity and low electrical resistivity. So you can read data in two ways. You can basically optically read data by shining light on this thing and figure out where the reflections essentially, or by determining the resistance, by passing current and determining the resistance essentially through this device. So there are two ways of reading. And both ways of reading are used, except the optical reflexivity way of reading is used in rewritable CDs. Rewritable CDs actually use phase change material, but these are old. Maybe none of you actually use rewritable CDs, but that's a very slow reading process. Now, more recently, people, especially at IBM, Intel, and Micron, they've invented ways of reading the cell by determining its resistivity, resistance levels. And by determining the resistance levels very quickly, you can read the cell reliably. And that's why this became very, very interesting recently. And you can store data as high resistance and low resistance, as you can see over here. I'm not going to go through the details of how it's really built, but you can read papers related to it. And if you're interested, actually, you can read one of the very early papers, architectural papers that were written on this topic that we wrote about now 12 years ago. And this is an easier to access version of it if you're interested. But this technology is real, actually. Intel Optane persistent memory was introduced in 2019. This was also introduced as a storage technology earlier than 2019. But basically, this is non-volatile main memory. This is a persistent memory. It's based on what Intel calls 3D X-point technology, but fundamentally, it's phase change memory internally. And you can see that it's a huge memory chip, 128 gigabytes over here. Oh, sorry, somehow it moved. Okay. Okay, let's see. So we're almost done. But you can do the same analysis between DRAM and phase change memory as well. And let's take a look at that analysis. So compared to phase change memory, DRAM is faster access, actually. Capacitor and slower PCM is slower access because of the materials, etc. Especially write access are actually much slower because you need to melt some material to change its resistance state, essentially. But we're not going to go into the details of it. But it's higher density. Phase change material is actually more scalable, so it's lower cost. So you can get higher density and lower cost as a result. DRAM requires refresh. Phase change memory doesn't have a need for refresh. It's non-volatile. So that's great. It gets rid of the refresh problem. Manufacturing is hard for both of them. In DRAM, manufacturing requires capacitor and logic together. In phase change memory, manufacturing requires less conventional processes, and it's also less mature at this time. Now, DRAM is volatile. It loses data at loss of power. PCM is non-volatile. So it does not lose data, right? This should be does not lose data. I don't know why it loses data over here. And this is good because now you can actually power things off and your data still remains in memory. And that could be a good thing or a bad thing depending on what you use that memory for, right? So downside of phase change memory is it has endurance problems. DRAM doesn't have endurance problems. And a cell cannot be used after n writes, basically. And that's a downside, basically. It's an endurance problem. You degrade the quality of the cell as you write to it. And that's why this cannot be an easy to use memory technology, at least that can replace DRAM completely today. And also one other downside is higher access energy. Again, I don't know why this is green here. So I'm online editing my slides as well, but you can see there are other trade-offs also that come into play. DRAM has lower access energy and PCM has higher access energy. So all memory technologies have these different trade-offs, and no memory technology is green at everything, basically. As you can see, different memory technologies are green at different things and red at different things. We've seen with DRAM and SRAM. Now I've shown you DRAM and phase change memory. But think about this when we talk about memory hierarchy and caches in the next lecture, because memory hierarchy will be mainly about deciding which technology to use at which level and how much of it to use at which level and how to manage it as well. And that's going to be increasingly important going into the future because one memory technology is not suitable for everything. Okay, with that, we're almost at the end. If you're really interested in emerging memory technologies, we're not going to cover it in this course because we don't have time, but we have the master's class that covers it in a lot more detail, multiple lectures, actually, as you can see over here. We talk about its implications on systems and storage systems and memory systems as well as applications, but we don't, as well as computing in memory also, but we don't have time for it. And there's a lot more on memory technologies. There's other things that we did not talk about, like scaling properties that is shown on the slide, but we don't have time to talk about it. But I'll invite you to take a look at future lectures or take future classes because memory is actually a very rich topic. And today, because it's the major bottleneck, there's a lot of innovation going on the memory side. If you think there's a lot of innovation going on the compute side, memory side innovations are accelerating even faster than the compute side innovations. And to conclude, there's a lot more to say about memory, but we don't have time. And if you're really interested in thinking about how to better design systems by not making the memory bottleneck, making memory as a first-class citizen, let's say, making it more central to the systems we design, I'd recommend you take a look at this particular tutorial that I delivered, which hopefully is accessible. It's a bit long, but it covers a lot of interesting topics. And there are also papers that are linked from the tutorial. Okay, with that, I think we're done. If there are any questions, okay, there's one question that I'm going to handle, but If there are other questions, please let me know as well. Okay, so as a non-volatile memory, wouldn't Optane be an alternative to SSD? How does it compete against current SSD? So that's a great question, basically. So actually, Optane, which is 3D export technology, which is phase change memory-based technology, it was first introduced as an SSD, and you can buy products in the market also as SSDs as well. And it's quite competitive with current SSDs. And we actually have some paper coming up, which Geraldo is working on, which we will put on archive soon, that shows that in real systems, it's actually faster, much faster than current SSDs. So from an SSD perspective, you can actually do the same comparison that I did, DRAM versus phase change memory. You can do the same comparison between phase change memory and modern and NAND flash technology. And we do it in some of the later courses that I mentioned over here. But certainly it's much more competitive compared to a storage technology like flash memory. So it could be used. It could be used certainly to replace or augment storage. But the interesting thing about this phase change memory is it could also be used closer to DRAM. That's why I think this is a very interesting technology. And it has some benefits over DRAM, but also some clear downsides of DRAM. So compared to DRAM, it's not as clear whether it can directly replace DRAM, because DRAM has a lot of good upsides compared to phase change memory. But compared to a conventional SSD, even a high performance SSD, it's actually quite competitive and better. So that's a very good question. So there's one more question. Is it also vulnerable to some kind of RowHammer attack? So that's another excellent question. So I believe internally, yes. But so RowHammer attack is an example of a disturbance, read disturbance error. Disturbance, what does that mean? Whenever you're accessing some memory cells, you're disturbing some other memory cells. And this fundamental disturbance phenomenon is actually very fundamental. It happens in hard disks. But hard disks have a lot of error correcting codes, so that they correct a lot of these errors before they supply data to you. That it happens in flash memory today. Actually, we characterize flash memory a lot to understand those read disturbance effects. So it certainly also happens in phase change memory. It also happens in SRAM. It happens in any memory technology as long as you make the memory technology small enough, because you have interference between the wires, as well as between the wires and the cells. So certainly, it's vulnerable to the disturbance effect. Now, whether you can exploit that disturbance effect as a security attack that can take over the system, that's a much more difficult thing. You can, for example, you can try to exploit that in flash memory drives. In fact, we did that, but it's not easy because flash memory drives has a lot of levels of protection and error correction. Even though read disturbance effects is real and it happens, a lot of the errors get corrected and they don't get exposed to the user. The fact that RowHammer happens in DRAM and you can exploit it is true because DRAM gets directly exposed to the programmer. So there are two issues. First of all, DRAM memory directly gets exposed to data structures, system data structures, programmer data structures, any user data structures, everything. So you can actually destroy data directly. And the second is, in DRAM, traditionally, there has not been much error correction because people thought DRAM is the perfect memory technology and you didn't need a lot of error correction. In fact, consumer systems have no error correction. Increasingly, people are adding error correction, but people are also finding that you can circumvent the error correction to do RowHammer attacks. So basically, DRAM is very special because of these two reasons. And as a result, you can launch RowHammer attacks. So the fundamental RowHammer phenomenon exists in any other memory technology, but you may not be able to launch RowHammer attacks on them because of the fact that those bit flips are not immediately visible. And also they are corrected before they become visible at all, if they at all become visible, basically. So these are very good questions, actually. Good that you're thinking. Okay, I think we're done unless there are more questions. I'll wait for 30 seconds and it doesn't look like there are questions. So have a good weekend, stay safe, and I will see you next week when we will start with the memory hierarchy. Take care.